Thank you for attention. A really special opportunity. I want to talk about recent success. Actually happened last month. We really had a great demonstration in realistic conditions of regenerating dialysate. So jump to that at the end. I'd like to thank the team, Go Zheng's in the front of the audience here, Yushi, Hao, and Mingwan, and of course the rest of the CDI team. Okay, I don't have to tell this audience that kidney dialysis, though life-saving, has some inherent problems that we really need to solve, and it's been stagnant for decades and decades. And as Buddy alluded to, the blood interface and connection is one of the key things we need to solve. But another one is the dialysate regeneration. Now, we use about 120 liters during a session, and you cannot carry that on your back. So if you ever have a hope of getting to portable dialysis, we need to regenerate the dialysate. And it turns out this is a pretty tricky problem that was largely addressed back in the 70s, the READY. So you can see this looks like a relatively compact device. And there's a really interesting cartridge right here stacked like a Devo hat, I like to refer to that. But basically this works by, we first have activated carbon, and then we have an enzyme to convert the urea to ammonia. And ammonia is very toxic to the body, so we have to ion exchange that out. And so we end up exchanging salts for ammonia. So we have to get our salt balance back in order. And also these cartridges are relatively expensive. So our commercial RO membranes have really dominated. But it does have the disadvantage of 120 liters per session. So we have to really think about, can we have a whole new technology to regenerate the dialysate? I'd just like to point out that urea is kind of devilish. It is just a surprisingly inert substance. Very few things, it doesn't stick to activated carbon, and it is fairly chemically inert, even though it is a relatively high energy molecule. So people have been working very hard with electrochemical oxidations. And a key problem is we have lots of bad oxidative species, in particular chlorine or chloride ions, sodium chloride going to chlorine gas and bleach, basically. And a lot of people worked hard on different absorptions, but it's just really devilish problem. So I'd like to look outside, what's been done, and actually we can go to the wastewater treatment people. And they had found a really nice technique where we can use a TiO2 and excite it by UV light. And this very selectively converts urea to dinitrogen gas and CO2. So both of these are very safe. And a key invention or breakthrough here was you really broke the circuit into a cathode where you have the oxidation, and on the other side you finish the electrochemical reaction and just split water. And a key innovation here was adding bubbles. That really made it work. However, just skip to the bottom down here, it was only 0.1% input current efficient. So they need 1,700 amps to be able to hit the target of a normal 15 grams per day for a patient. And so this is completely unrealistic, not feasible. But when we really look at it, there was room for improvement. The quality of the TiO2 they were using was rather poor, just particles, paste put on a conducting slide. And here we were able to, in the literature, saw people were able to grow nanowires directly connected to the conducting substrate. And this is one of the key breakthroughs we had here, is that we were able to apply voltage so we could separate the electrons in holes. The holes do the oxidation of the urea, and the electrons go back and complete the circuit. Another big innovation was adding an air-breathable electrode that's commonly used in the fuel cell world. So it has platinum particles on carbon, so it can do the other half of the reaction. And then finally, we have efficient LED technology. So by combining the three things, we actually got huge improvements in performance, orders of magnitude. So in our study, we were able to decompose 15 grams per day of urea from a normal patient, and with 11 amps versus the 2,000 thereabouts. So we finally got something that is really quite practical. So with scale up, basically what we have flow channels, so we can flow the dialysate through, and we can see the LED right here illuminates the TiO2, which oxidizes the urea, and over here we have the rest of the reaction happen, the splitting of water. And roughly we'll need about 1,800 square centimeters. It may sound like a lot, but that's just a couple square feet. And basically, if we could stack 3 of these panels right here, it could fit inside a backpack. So it's realistic to get this to become a portable device. Obviously, we'd like to go for carry-on suitcases first and iron things out, but this is a feasible size and efficiency. Okay, so another piece of the puzzle, though, is unintended byproducts. That if you have very complex blood chemistry going into an oxidation cell, you'll make complicated oxidation byproducts. And we did a very careful analysis of what's present, and what we can see is there's a fair amount of non-urea uremic toxins, roughly 8 grams per day, need to be removed, or I'm sorry, this is per session, and urea is on the order of 23. So we have about 25% of its other ones. But really the big problem is glucose. We need sugar to operate, and we're up at equal concentrations with urea. So we need to find a way to protect our oxidation unit from the other chemistries. So in order to do this, we're proposing a 2-loop system. So this was the prior ready system, which had the catalyst, enzymes, and ion exchange. But in our case, we'll just have activated carbon in this loop, and then we need a urea selective membrane. And this will allow just urea to go into the oxidation unit, and we can very efficiently do the dialysate regeneration. But the thing is, we need this kind of magic membrane that will allow urea to go through. And it turns out a big problem in the wastewater world is urea. That people try to purify wastewater, but urea gets through and you don't want to drink that water. But in this case, it's if life gives you lemons, make lemonade, that we can use this urea selective membrane to highly efficiently pass urea to our oxidation system. So sure enough, urea gets through, and we test a whole bunch of other chemicals, many orders of magnitude less flux. So this is very urea selective. And just point out, we used a commercially available forward osmosis membrane. And we'll learn more about technology where we can have urea selective membranes next. So basically, we measured the flux through this membrane, and it hit the marks very easily. So this would be a urea removal grams per day or a mass transport coefficient, and we're well above the 15 needed. So this technology would work great. And just try to show you the mass balance an engineer likes to do is we're going to take X moles out of the bloodstream. It'll go into our dialysate, add the X, but we'll remove it in this other membrane, and then the pore will destroy it. So we kind of have mass balance through here, and the membranes hit the mark. So we did a nice scale up, and this is really new data where we actually scaled it up to be the relevant 15 grams per day. And so again, we have our 3 loops, the patient, the dialysate that we're regenerating, and then the oxidation loop where we want just urea to go in there so it is efficient. And I'd like to point out a key thing here is we use realistic conditions. We had bovine cow's blood here, 5 liters representing the human body. And then we used commercially available dialysate bags. So this is the real solutions that we're working with, not just the simple models. And over here is our pore unit. We have 8 of these panels that are roughly this big, and measuring the concentrations as we go along. So basically our target is to try to keep our patient at a level 10 millimolar of urea, and we measured each of the loops, and we can see we kept very close to that goal. And another thing we need to worry about, not just urea, is can we get rid of the other uremic toxins with activated carbon? And in this case, we use a creatinine to represent everything else, and we were able to keep these constant levels here in the patient. So both the activated carbon that had been used for decades did their job, and our pore unit did its job because it was protected. Okay, so as conclusions, photo-oxidation is a very powerful, selective way to oxidize a urea to safe nitrogen gas, not producing ammonia. We're roughly at 0.6% conversion, so very safe levels of ammonia. We have prototypes that reach the daily clinical needs under realistic conditions, where we're actually using blood and a real dialysate. The key component here is this forward osmosis membrane to help protect the cell. Activated carbon is also a key component to absorb the non-uremic toxins and also just get rid of any other oxidative products over here. Okay, and what we'd like to point out here is that if we look at just the core components, the pore panels and the two membrane dialyzers and activated carbon, roughly it would occupy 25% of the volume of a standard carry-on suitcase. So we're getting really close to this concept of portable dialysis that you can take with you and be part of your daily life. Okay, and again, thanks for the entire team. It was really a big heroic effort to get that last pilot plant done. Right. Thanks for your attention.